this lesson kind of wraps up all the probability rules we're going to be using. And the main ones we sort of focused on were simple probability, how to find the probability of something not happening or the complement, how to find the probability of one event or another happening, or means what mathematical operation? Add. And then we did the probability of some event and some other event happening, and means multiply. So just remember that. So we're going to talk just a little bit more about some multiplying questions. So successive events, independent events, which means that one event does not depend on what happened in the previous event. Okay? So events are successive if one happens after the other, or if it's a repeated process. And remember, we talked about independent events. Knowing the outcome of one event does not affect, it does not impact the probability of some other event. Okay? So like, for example, if you flip a coin and then roll a die, those events are going to be independent. Okay? Because whatever you get on the die does not depend on what happened on the coin flip. Okay, so let's say we've got a coin. We're going to flip it 5 times. What's the probability we get heads 5 times in a row? So you can look at this using what we did last time, a tree diagram. So the first flip, you're going to have heads or tails. And let's just focus on heads. Well, what's the probability of getting heads on the first flip?
50.
0.5, or 50%. Okay. Let's say we get heads. Second, we can get heads or tails. What's the probability of getting heads on the second?
50.
50 again, and then that keeps happening 5 times. Now, obviously, there's other branches, but we're only going to focus on ones where heads occurs 5 times. Tails, tails, and so on, and then there would be other branches. Okay? So if we want to find the probability of heads and heads and heads and heads and heads, what do I do with all these 0.5s? Multiply. So the probability is going to be 0.5 times 0.5 times 0.5, or what's an easier way to say it? Yeah, I might as well just do that. That's going to give us about, that doesn't seem right. Did I make a mistake in my notes? 0.5 to the 5th? That's not 0.3. 0.03125. I don't know why I put that in there. 0.3125. Or just a little over 3%. Okay. So if we've got successive events, I mean, like I said, you could always use a tree diagram. But if you're doing a bunch of successive events, it just involves multiplication, and you can write it using exponents. Okay? So let's look at another example. Free throws in basketball. So one of the NBA's best free throw shooters is Steph Curry. He makes 90.6% of the free throws he attempts. Assume each free throw attempt is independent, which means one free throw does not depend on what happened on the previous free throw. It's always 90.6%. What's the probability he makes 6 free throws in a row? How would you find that?
90.6.
Don't think in decimal all the time, or don't think in percent all the time. 0.906 to the power of 6. Yeah, because if you do 90.6, you're going to get a huge number,
Right.
which doesn't make sense. And again, I'm just going to do this so I don't. Oops. 906 raised to the 6th. Yeah, that one's okay. So it's approximately 0.553. Then you can convert it to decimal if you want, or about 55.3%. So a little over half. Okay, which is pretty good. All right. So Steph Curry is fouled in many three-point situations, so he often takes 3 free throws at a time. When he takes 3 free throws, what's the probability he makes the first 2, but misses the last one? So think of it this way: makes and misses. So what's the probability that he makes?
0.9.
And makes. Translate that. Or square, sure. And misses.
9 times 0.0.
Times 0.0894. Right. So makes, misses. And then when we calculate that, we should get approximately 0.077, or about 7.7%. Okay, so that's how we deal with successive events. We use multiplication. And depending on the question, it could be taking the probability of something happening and then multiplying by itself repeated times, or it could be a combination of making something or an event happening and then event not happening and then event happening, whatever, but we still multiply. Okay? Couple last things. At least one. This you got to think about a little bit. Okay? So we're back to Steph Curry again. We know he makes 9.6% of the free throws he attempts. And we assume that they're independent. What's the probability that he makes at least one of his next 4? Well, that could get a little crazy, because think of all the possible combinations where he makes one. Like he could make the first one and then miss 3, right? He could miss the first one, then make, then miss. Okay, these are all situations where he does 1. But it said at least 1. So what about all the situations where it's 2? So he could make, miss. He could make, miss, and you can keep listing a whole bunch of different possibilities. The point I'm trying to make is it's not good to do it that way. Okay? We need another way to do it. And the best way to do it is, let's consider the probability that he misses them all. Because think of all the situations. What are all the possible situations? He makes them all. He makes 1. We don't know what position that 1 is. He makes 2. He makes 3. He makes all 4. Okay? No. Did I do that one already? Okay, makes 1, makes 2, makes 3, makes 4, and then makes none or misses them all. So why don't we find the probability that he makes none? What would that be? How would I find that?
0.0943.
So we would have to do 1 minus 0.906 and then raise that to the 4th. Because this is the probability that he misses, and this is the probability that he misses 4 times in succession. So when we do that, we get, so I did so 0.094 raised to the 4th is about, oh, I got scientific notation. So 0.123478. So I got that right? Let's see. Yeah, I got that right. So it's about that. Very small. Okay. So that's the probability that he makes none. But all the other situations are he's making at least 1, isn't it? Like he'll make 1, he'll make them all, he'll make 2, he'll make 3. Okay? So to find the final probability, I have to do 1 minus what I just found here. 0.0000078. And when I do that, 1, 2, 3, 4, 7, 8, I get 0.9949s, 2 2s, or about 99.9%. Which makes sense because it's a very small probability that he misses them all or makes none. Which means the probability that he's made 1 or 2 or 3 or all 4 must be really, really high. Okay? So be careful with that one. And the trigger for that kind of situation is, it'll always say in the question, what's the probability of at least? As soon as you see at least, it's this method. Okay? So the probability of at least 1 is always 1 minus the probability of none. And then finally, we're going to get into this a little bit more. And we talked about it when we talked about independent versus non-independent events. Sampling without replacement. And I did that with the card the other day. I showed you, you guys calculated a probability for me when I replaced the card, and then you calculated a probability for me when I didn't replace a card. That would be sampling without replacement. So here we have an example. We've got a jar with 12 blues marbles and 8 red marbles. We're going to sample without replacement, which means as soon as we draw one out, we're keeping it out. Okay? So I want to find the probability that we drew a blue, kept it out, then drew a red, kept that out, and then drew a blue again. So again, you should be thinking blue and red and blue. And when I keep saying the word and, it's multiply. Okay, so what's the initial probability of drawing a blue when all 20 marbles are in? 12 out of 20. And a blue marble has now come out. So what's the probability of drawing a red? There's still 8 reds in there, but there's only 19 total marbles. Then a red came out. So we got a blue out, a red out, What's the probability of blue?
11.
11 over 18. And then you would simply multiply those together. And you would get an answer of approximately 0.154. Or again, if you want to say it as a percent, you don't have to. 15.4%. So those are the probability rules. We finished the unit with something called probability distributions that we're going to do over 3 lessons. And just as a bit of a preview, I'm not going to worry about the discussion. Okay? Here's the idea of a probability distribution. You roll 2 dice. What are the possible numbers you could get from smallest total to largest total when you roll 2 dice? 2 up to 12.
My bad. 12.
So we can get 2, 3, 4. That's okay. Remember, a distribution is sort of a picture of all the data values, right? So if you think of probability, like what would be the probability of rolling? Do you know what boxcars is? 2 ones. What would be the probability of rolling a 2? Low or higher? On the low side, right? You'd agree? Same with this. Okay. But because there's only one way, and by the way, when you roll a pair of dice, there's 36 possible outcomes. Because for the first die, you could get 1, 2, 3, 4, 5, 6. And then for each of those, like if you roll a 1, there's 6 possibilities for the second. If you roll a 2, there's 6 for the second. So 6 times 6. So there's only one way to get this. And there's only one way to get this. What's the sum that occurs the most according to probability? 7. Because you can get 7 6 ways. 6, 1, 1, 6, because order does matter. 5, 2, 2, 5, 4, 3, 3, 4. So if you kept rolling over and over and over and over again, eventually it's going to look like this. I got a little smiley face. It's like we're looking at the clouds, we see that. Okay. But you can see that it actually takes on a normal distribution. Because if you keep rolling and rolling and rolling, the 7 should be appearing the most. Okay. And these should be appearing the least. Unless it's a loaded die or something like that. Okay. So that happens in a lot of probability situations. Sometimes in probability situations, it looks like this, where the probability of something happening early is the highest, but happening later is lower. And we're going to talk about that type of probability. But that's what we're going to kind of move on to. And then once we do that, we're ready to start inferencing. Okay.